Hello, friends. The speed of light is one of the most fundamental constants in the universe. It is not merely a limit for light itself, but a cornerstone of modern physics that influences various phenomena, from the behavior of time and space to the fundamental laws governing the cosmos. Understanding the speed of light opens the door to a deeper comprehension of the universe and the exploration of new frontiers in science and technology. Light is an electromagnetic wave that travels through space at an astounding speed of approximately 299,792,458 meters per second, commonly referred to as the speed of light. This speed is not only a characteristic of light itself, but also a fundamental property of the universe. One of the most intriguing aspects of light is its wave-particle duality, a concept in quantum mechanics where light is described as being made up of particles called photons. These photons have no mass and always travel at the speed of light, regardless of the observer's frame of reference. Albert Einstein's theory of relativity revolutionized our understanding of time and space. According to Einstein, the speed of light is the ultimate speed limit in the universe, and nothing can travel faster than it. This principle leads to some mind-bending consequences such as time dilation, where time appears to slow down for objects moving close to the speed of light relative to a stationary observer. Einstein's special theory of relativity also introduced the famous equation E=mc², which describes the equivalence of energy and mass, with the speed of light squared as the conversion factor. This equation highlights the immense energy contained within a small amount of mass, and has been instrumental in understanding nuclear reactions and the energy produced by stars. Gravitational waves are ripples in space-time caused by the acceleration of massive objects like merging black holes or neutron stars. Predicted by Albert Einstein in 1916 as part of his general theory of relativity, these waves travel at the speed of light and carry information about their origins and the nature of gravity itself. Unlike electromagnetic waves, which can be absorbed or scattered by matter, gravitational waves pass through matter almost unimpeded, making them ideal messengers from the universe's most energetic events. The fact that gravitational waves travel at the speed of light is deeply intertwined with Einstein's theory of relativity. According to relativity, the speed of light is the maximum speed at which information can be transmitted. This means that gravitational waves, like light, provide information about events that occurred in the distant past. Massless particles are elementary particles that have no mass and always travel at the speed of light in a vacuum. The most well-known examples of massless particles are photons and gluons. These particles are fundamental to our understanding of the universe, as they mediate the electromagnetic and strong nuclear forces, respectively. Because massless particles have no mass, they are not subject to the inertia that affects massive particles. This allows them to travel at the maximum speed possible in the universe, the speed of light. Photons are the most familiar massless particles. They are the carriers of the electromagnetic force, which includes light, radio waves, and X-rays. Photons are responsible for the interactions between charged particles, such as electrons and protons. The fact that photons are massless allows them to travel at the speed of light, making them the fastest means of transferring energy and information. This property is crucial for technologies like telecommunications, where signals are sent over long distances using light waves. Photons' ability to travel at light speed also allows us to observe the universe. The light from stars and galaxies reaches us across immense distances, providing a glimpse into the past and allowing us to study the cosmos. Gluons are massless particles that carry the strong nuclear force, which binds quarks together within protons and neutrons. The strong force is the most powerful of the four fundamental forces, but acts only over extremely short distances. Gluons' massless nature and light-speed travel allow them to mediate this force effectively, holding atomic nuclei together. Unlike photons, gluons can interact with themselves, leading to complex interactions within the nucleus. This property contributes to the confinement of quarks, ensuring they remain bound within protons and neutrons. Massive particles are particles that have mass and make up the matter we encounter in everyday life. Examples of massive particles include electrons, protons, neutrons, and larger composite particles like atoms and molecules. Unlike massless particles, massive particles cannot travel at the speed of light. The speed of light acts as a cosmic speed limit for these particles, meaning they can only approach but never reach the speed of light. Albert Einstein's theory of special relativity explains why massive particles cannot reach the speed of light. According to this theory, as a particle with mass accelerates and approaches the speed of light, its mass effectively increases, requiring more and more energy to continue accelerating. Special relativity also introduces the concept of time dilation, which affects massive particles traveling at high speeds. As a massive particle approaches the speed of light, time for that particle appears to slow down relative to a stationary observer. This means that processes occurring within the particle, such as decay or interactions with other particles, will take longer from the perspective of an outside observer. Time dilation has been confirmed through experiments with high-speed particles, such as those conducted in particle accelerators. For example, particles known as muons, which have a very short lifespan, live significantly longer when traveling at speeds close to the speed of light compared to when they are at rest. The speed of light is not just a limit for physical objects, but also for information. According to Einstein's theory of relativity, the speed of light is the maximum speed at which information can travel through the universe. This means that any signal or message sent from one point to another cannot travel faster than the speed of light. This speed limit applies to all forms of communication, including electromagnetic waves like radio signals, light waves, and even potential quantum communication methods. This constraint ensures that no information can be transmitted instantaneously across distances, maintaining the structure and causality of the universe. Causality is a fundamental principle in physics that refers to the relationship between cause and effect. It dictates that a cause must precede its effect in time, and this sequence cannot be violated. The speed of light plays a crucial role in preserving causality across the universe. By limiting the speed at which information can travel, the speed of light ensures that cause and effect relationships are maintained, even over vast distances. This principle of causality is essential for the consistency of physical laws and our understanding of the universe. The speed of light as a cosmic speed limit has profound implications for our understanding of the universe. It means that no information can be transmitted faster than light, ensuring that signals and messages are bound by the same constraints as physical objects. This limitation affects various aspects of physics and communication technology. In quantum mechanics, the concept of quantum entanglement allows particles to be interconnected in such a way that the state of one particle instantly influences the state of another, regardless of distance. However, this phenomenon does not violate the speed of light limit because no information is transmitted in the process. The limitation of information transfer to the speed of light has practical implications for modern communication systems. Technologies that rely on electromagnetic waves, such as fiber optics, satellite communications, and radio transmissions, are all constrained by this speed limit. As a result, the speed of light influences the design and operation of communication networks, affecting everything from internet speeds to data transmission across the globe. In the context of global communication, the speed of light introduces latency or delay in signal transmission. While this delay is negligible for most everyday applications, it becomes significant in situations involving long distances, such as intercontinental data transfers or communication with spacecraft. Quantum entanglement is a fascinating phenomenon in quantum physics, where two or more particles become interconnected in such a way that the state of one particle instantly influences the state of another, no matter how far apart they are. This mysterious connection occurs because the particles share a single quantum state, meaning their properties are linked regardless of the distance between them. Quantum entanglement was first described by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 in what is known as the EPR paradox. Einstein famously referred to it as spooky action at a distance, as it seemed to defy the principles of classical physics. The expansion of the universe is a fundamental concept in cosmology that describes how the universe has been growing since the Big Bang. This expansion means that galaxies are moving away from each other over time, leading to an ever-increasing distance between them. The speed of light plays a crucial role in understanding this phenomenon, as it sets the limits on how we observe the universe and its expansion. The universe's expansion was first observed by astronomer Edwin Hubble in the 1920s. He discovered that galaxies are moving away from us and that their speed is proportional to their distance from Earth. This relationship is known as Hubble's law, and it provided the first evidence for the expanding universe. The speed of light is a fundamental constant that determines how we perceive the expansion of the universe. Because light travels at a finite speed, it takes time for light from distant galaxies to reach us. This means that when we observe distant galaxies, we are seeing them as they were in the past, not as they are today. The finite speed of light creates a cosmic horizon, which limits how far we can see into the universe. This horizon is known as the observable universe and represents the maximum distance that light has traveled since the Big Bang, approximately 13.8 billion years ago. The speed of light is crucial in shaping the structure and behavior of the universe. It defines the cosmic speed limit and influences how we perceive time and space. The finite speed of light means that when we observe distant objects in the universe, we are essentially looking back in time. Light's role in the universe extends beyond its speed. It is a primary means of transferring energy across vast distances and plays a vital role in processes like photosynthesis, which supports life on Earth. Additionally, the study of light and its interactions with matter, known as spectroscopy, provides critical insights into the composition and behavior of stars, galaxies, and other celestial bodies. The speed of light is a fundamental constant of the universe, but scientists and engineers are exploring theoretical technologies that might one day allow us to exceed this cosmic speed limit. Concepts like warp drives and other advanced propulsion systems capture the imagination and hold the potential to revolutionize space travel. The idea of a warp drive is rooted in the science fiction concept of bending or warping space-time to achieve faster-than-light travel. In theoretical physics, a warp drive would work by contracting space in front of a spacecraft and expanding it behind, effectively allowing the ship to move through space faster than light without violating the laws of physics. The speed of light is not just about light. It is a gateway to understanding the universe and exploring new frontiers in science and technology. It influences various phenomena, from gravitational waves and quantum entanglement to the expansion of the universe. As we continue to push the boundaries of what is possible, the speed of light serves as both a limit and an inspiration, guiding us toward new horizons and a deeper understanding of the cosmos. Whether through the development of new propulsion technologies or the exploration of light's impact on our understanding of reality, the journey to understand and utilize light is a never-ending adventure that promises to transform our world and beyond. Thank you for joining us on this journey through The Speed of Light is not just about light. Please like, comment, and share the video, and please do not forget to subscribe for more videos.